we're going to talk about building a modern app at cloud scale using containers and data services. Okay, so we're just going to go through roughly what is the process, why even use containers, and why think about data services, right? And please ask questions. It's always a lot more fun for everybody, including myself. Like, if you guys ask questions, otherwise, I might be sleeping. I don't know. So, okay. A rough agenda. So if I really bore you guys to death, you know when it'll finish. First thing is very quickly who we are, what we do, and then why microservices and containers. After that, like how do you do data management when you try to build apps using a microservice architecture? Finally, we'll do a live demo. We'll do a demo of a completely containerized end-to-end stack of an e-commerce app, and we'll open it up for questions, but please don't wait till the end. Okay, myself, Karthik, Kannan, Mikhail, and a whole bunch of others like Ram here, a whole bunch of us, we work at Facebook building microservice-based architectures and apps and putting that into production. So it's kind of funny, when we started at Facebook and in the early days of Facebook, everything was not containerized. It did not run using a microservice architecture. It was a gradual evolution, like based on the need, right? And that's the need that the rest of the world is also seeing. Anyways, the kind of applications that we built on top of the NoSQL platform we supported, which was H-based, was things like Facebook messages, where we got like billions and billions of messages flowing in when every person would try to talk to another, be it a chat, an SMS, or an actual message on the Facebook application itself. We stored all of that in H-based. We also stored in real time the search index, and search index is very explosive in its volume. So every message, you write a 10-word message, every word gets inserted in the reverse index. So it's very explosive in terms of how many writes you have to take. Similarly, we were also the data store for the alerting system called ODS, Operational Data Store, where you did alerts, TimeSeries data, so on and so forth, and that can be fairly write-heavy and read-heavy. Billions and billions of data points flowing into the database. And finally, real-time systems such as spam detection, where you track activity of users and you try to figure out malicious users so as to protect your experience on Facebook. And we used to detect tens of thousands of accounts, but the data was stored on Facebook and it was analyzed in real time. So think of that as closer to your real-time personalization, AI, ML, that kind of workload, right? Okay, so very quickly, we're going to touch on what Yugabyte is, because we're going to use it towards the end when we see the demo, and then we'll jump right into how do you build using containers and why, and so on and so forth. So Yugabyte was built with 3 core design principles. It's transactional, it's high performance, and it's plan scale, right? And of course, the 2 deployment principles, which are cloud native and open source, right? So on the transactional side, it supports distributed transactions. So it's just like Google Spanner. So when you need it, you have multi-row atomicity, but it also does a lot of work to make the single row flow extremely performant. And we'll talk about that. The second piece is, at its core, it's a document-based, strongly consistent store. So it's very easy for us to expose document and JSON-style objects and support a variety of different API access patterns on top. On the performance side, even though it supports distributed transactions, it's completely possible for your workload to have a single row consistency requirement, and this is a majority of most workloads in most applications. So it supports extremely low latency tunable read, so you can read from the nearest data center, read from the absolute source of truth, so on and so forth. So we'll see examples of those. And it supports high throughput, so you can make Yugabyte a target for a streaming ingest, and it will do extremely well. So it can take a large batch read and batch write and perform well. Finally, on the planet scale side, Yugabyte internally supports as a first-class citizen global data distribution. So if you want your replicas to exist in faraway regions, different clouds, a hybrid deployment with some data on-prem and some data in the cloud, so on and so forth, all of that is supported. And it automatically shards and rebalances data. On the cloud native side, we had the luxury, we started building this 2 years ago. Containers were already a well-known thing at that point. So it's built for the container era. Yugabyte works in VMs, bare metal, and containers, but most importantly, it's built with the elasticity of containers in mind, so it can really exploit the container ecosystem well. And it's self-healing and fault-tolerant. It's what you would expect from a replicated database in this day and age. So it's self-healing, fault-tolerant, but offers you strong consistency in the face of those failures. And it's open source under Apache 2.0. We have a GitHub project. Feel free to follow us, watch us, star us, and show your support if you like what you hear. But the second aspect to open sourcing is we're not just open source, we also support open source APIs. So some of the popular APIs we support are Apache Cassandra. So you can use an Apache Cassandra client driver and point it at Yugabyte, and you'll be able to read and write data from Yugabyte. Similarly, you can use a Redis client from the open source, and it's going to offer you a persistent elastic store, but it speaks Redis on the top. And we're working on Postgres. In fact, our 1.0 is coming out like in a week or so, and we're going to be announcing our beta support for Postgres pretty soon. Okay. The three APIs we talked about: YSQL, so Yugabyte Cloud Query Language. So these are the ways you interact with the database. So Yugabyte Cloud Query Language, which is completely Cassandra compatible. In fact, we've extended the Cassandra query language to add things like transactions. So you could do begin transaction, you can write a whole bunch of rows and then finalize that transaction and have it atomically appear like as one unit of work. Similarly, we support secondary indexes built on top of distributed transactions for consistency. We've also extended and added a JSON data type that's native. So these are all extensions on top, right? But it's a well-known data model, and it's something that most people are familiar with. The second API that we talked about is it's completely compatible with Redis. We call this Redis, Yugabyte, like the Yugabyte, like Redis API supporter on top of Yugabyte. So it's the remote dictionary server that Yugabyte runs. It's a distributed transactional key value store. It's scale out if you want, like you'll just be able to add nodes pretty easily because it is a true replicated distributed database. It's automatically sharded and it rebalances itself. So folks who work with Redis, I don't know how many folks have worked with Redis, by the way. Yeah, so you guys know that you have to manually shard your data, you have to persist it behind the scene, and you'll have to figure out which shard to write data to. And as you add more nodes because you want more, throughput or reads or writes, it gets a lot harder because the application has to move data between the different shards. In this case, you wouldn't have to do any of that. You wouldn't have to store your data because Yugabyte persists the data with strong consistency. And as you add nodes, it internally automatically scales up. We've extended Redis too. A lot of our customers and users were very interested in a data type in Redis where you can set your time to live, data expiry on individual attributes inside a collection instead of the entire collection. We're going to talk about that in a little bit, but this is an extension that you can find on Yugabyte, and that's the native TimeSeries data type. Finally, we're working on Postgres as a scale-out distributed database. So instead of having a single Postgres, and then when you want to scale out, you add a second one and you figure out sharding at the data layer. So this is something that we intend to do underneath the cover. So your Postgres database and tables and data will be able to scale out and get replicated to remote geographies and so on and so forth. Okay. Let's go quickly into the architecture. We talked about the three different APIs. Now, underneath these three APIs, you get uniform semantics of automatic sharding and load balancing. Okay, so it doesn't matter which API you come through, you get that. And the data is always persisted in a scale-out system. So we use commodity nodes, and you'll be able to continue to add more and more nodes. The data is sharded, so as you add nodes, it gets replicated, and the new nodes start serving reads and writes, and the process is really, really efficient. Now, in order to build the core of Yugabyte, on top of which all of these different languages are supported, we use a Raft-based replication. First time we're hosting, so. Okay, so where's that? Okay,
switch it on, switch it on.
Yeah, switch that on. All right, so we use a Raft-based replication engine for ensuring strong per key consistency. We have a per node doc.db. We call it a doc.db because it's a document core and it's transactional and it can model a variety of different workloads. So it's optimized for a variety of different access patterns. And finally, we have a global transaction manager that figures out single row ACID and multi-row ACID, and it figures out at what point, how much of performance can you get given the type of queries in a transparent fashion. So sometimes if you're doing distributed ACID transactions, there is laws of physics kick in and you can only go so fast. But if you're doing a single row ACID and there are no conflicts, you can go really, really fast. So that the global transaction manager figures that out. Okay. All of this runs on top of any IaaS. So it runs on top of a bare metal on-premise. It runs on top of VMs, whether it's in a public or private cloud, and it runs in a containerized environment. So it's pretty easy to get it to run anywhere. And finally, because of our commitment to stay completely API compliant with well-known APIs, we inherit the ecosystem around it. So that means you can write Spring Boot applications on top of Yugabyte. You can use like a Smack stack. We're calling it like a Sky stack. So Spark Streaming, Kafka, and Yugabyte. Those interplay pretty well together. Janus Graph for graph-like access, Kairos DB for time series, and so on and so forth. So we inherit the ecosystem from all of the APIs that we support. Okay, so that was the quick overview. We'll see a little more of it in a different angle when we take an actual application in context. But firstly, let's talk about why all this talk about containers and microservices and what's the big deal, right? Like maybe most of you guys know, but I'll be quick about it. Okay, so the cloud native revolution is happening. Everybody is going from the legacy enterprise to the digital enterprise, right? So no questions about that, right? Like everybody wants to have an online app for everything. It doesn't matter if you're Home Depot or you're Starbucks or you're like whatever. If you're not building that online app, somebody else will, and you're going to be out of business, right? So that's pretty clear, I think. In other words, Amazon will eat your lunch if you don't build it. So legacy enterprise has to go to digital enterprise, right? So they have to digitize. The minute that happens, cloud is a great place to be because every time your workload increases during Thanksgiving, everybody wants to come and buy your stuff, or like it's tax season, or it was like elections and you have to distribute news. You don't want to buy 10,000 servers and keep them around because you just need it for 3 months, right? And there's a variety of other reasons, like even operationally, why economies of scale kick in. So cloud native or going to a cloud is happening, right? At different rates and depending on the data sensitivity, at different, people have different thoughts about it. So the first thing that has changed is people used to have 1 or 2 data centers and everything would be built around that. The app would be built around that. Now you have about 100. Right? So you have all these regions across all these cloud providers. There's just a few that are named here, but there's so many of them, and you add your own private data centers to it, and that's what's accessibility, right? And it doesn't matter if you don't want to use it because somebody else will, and the users will get a better experience, and they'll go leave for that app. So it's just become a necessity to start using all these data centers effectively. Second piece is you had traditional servers. Now you're going to go into something that helps you move faster, whether it's a VM or containers. You should be able to spawn them faster. You should be able to update your software faster. You want to be able to utilize and burst quicker, so on and so forth. So a variety of reasons why you want to move fast, right? And in the container side, there's traditional Docker and Kubernetes, and then there are Kubernetes managed services that various public clouds are offering, and they all look pretty symmetric. But the point is, you want to be able to utilize more and more of this, right? And there's often interesting thoughts that people in different verticals have about which clouds they want to use and which clouds they don't want to use for a variety of different reasons, right? Like some of them may be regulatory and you will have to pass, HIPAA or whatever kind of compliance. Some of it may be I just don't want to feed my competitor by using his machines or his cloud, and so on and so forth. Now the third piece is when you're building an app, that also has changed because everything else has changed. You no longer build to monolithic application servers and so on. Your app is no longer monolithic. Everything is with scale up because when that huge demand comes in, you want to be able to address those users and you want to be able to service them. If you're getting like 1 million page views, you don't want to be going down because you're successful. You want to be able to somehow serve your pages, right? That's what you want to do. So for that, you have a variety of modern frameworks that people are moving to. So things like Spring Boot, Express, Node.js, Django, et cetera, et cetera. And application architecture itself has changed to make it more REST API based because you have to deal with a variety of mobile clients, browsers, desktops, so on and so forth. So there's a variety of different reasons why the app infrastructure has changed. Okay, so we talked about all of the stuff that will help you build an app and deploy it and run it and move it across different regions, manage it, and so on and so forth. But what about the data portion, right? The data portion is what nobody really talks about. So let's look at, now you have this app, but what do you do for the data? So what is pretty clear is the diagram on the left is how it used to be, right? There's a single database, there's a single app. You put everything in that app, it will manage all your session state, everything that you want. And the database has all the data. every single access pattern in that app, it doesn't matter whether it's a user liking a post or it doesn't matter if they're checking out on the cart, everything is built into one application server. Right? That used to be. But today, what people find is the number of people interacting through one access pattern increases dramatically. So the picture on the right, where one of the services is scaled out across 2 nodes, but the other services are still single. So that means you can actually go through each of these flows and scale them out independently. Right? That's what you want from the app layer. But that also means each of these different access patterns need to be able to scale the database layer, because it's not like you can just keep scaling the app infinitely. The database demand will also increase. And the type of apps that are being built, they have diverse and different requirements from the database itself. So that means each access pattern typically requires a different API and a different set of constructs for the data. Let's look at what that means a little more, right? If you're building an app, right, most of these things should be familiar to you you'll have come across this at some point. What do you do if you want strong consistency, right? So you generally go and pick an RDBMS system because NoSQL systems can give you, eventual consistency, and your data is not always accurate. What about ACID transactions? Most NoSQL databases, or all of them, don't support transactions. So if you want to do something like, I have a checking account and a savings account, I want to transfer $100 from the check to savings to the checking and not lose my money or not end up giving the other guy a lot of money, like I really want what I expected to happen, you pretty much have to go to an RDBMS. Secondary indexes, joins, like this list goes on, right? This is a variety of different, and if you look at this, different apps will need different features from the database. And so that means if you look at the table on the right, you pretty much need to piece together multiple different databases to build your app, right? And if it's all in the same database and you don't want to scale the database ever, great. You could have just put it in one of the RDBMS systems, never scale it, you're good. The minute you need to replicate, the minute you need to scale out, all of this starts mattering, and that's what got us to the state that we are in today, I think. This is how you would build an app if you hadn't thought through what happens with microservices and what happens as you scale and what are the complexities, right? So, and we look at a lot of these access patterns and show how we are helping address a lot of these access patterns. So we'll come to that in a minute. The second piece is, it's not just the app development, but at the time you're developing the app, you also need to think about what happens when you deploy, right? Especially around things like database A gives me certain guarantees when I scale out, but database B gives me different guarantees when I scale out. What your user doesn't care because it's the same data. It doesn't matter whether I'm seeing my name, user login and name and that stuff, or it doesn't matter if I'm seeing my profile or my history of all my orders that I have done. None of this matters. Like, to me, it's just data. A page has data coming from different microservices, each of them using a different database, each of which behaves differently. So that means you have to worry about things like linear scalability. Who can do it? Who cannot? Fault tolerance. What happens if the fault happens? Will I get back the same data, or will it say that data is no longer available and I have to kind of hide that in my app? So a whole bunch of these requirements also start kicking in. And if you go look at the matrix now, there's a bunch of features at the deployment, at the development time that traditional SQL gives you, but you don't have that at the deployment time. And there's a whole bunch of features that NoSQL gives you, but you don't have that at the development time. So it becomes a really complicated problem trying to build around the limitations of the database. So often what happens is, sorry, I can't build that feature. It'll take me another year. You really want it, or maybe not. Let's do this other feature and move on. So that's usually the trade-off or the compromise that's made, because it's tough. It's difficult to do that, and especially when the business is pushing for agility. Like, everybody wants to move fast, right? And like 1 year, I'll forget about it. Like, you don't even know if that feature will be relevant in a year or what will happen. Right? So that's typically the thought process going through. Okay, so what we've said is doing it right is accepting complexity. So let's take a simple e-commerce app. Right? We're going to keep revolving around this e-commerce app theme today, but you could pretty much substitute it with any app. It doesn't matter. The result is the same. And we're going to see a reference architecture and an actual demo. So you can just use that as an example. So let's say you have a bunch of products that you're trying to serve. Right? Some of the 3 simple microservices that you would have to put in. You have items. You have items and their description and how much, what is the cost of that item and so on and so forth. All of that goes into the items microservice. And because this data has to be extremely correct and extremely consistent, you put it in an RDBMS. I'll come to the middle one last. But the second one is, say the reviews microservice. People keep writing reviews, and you'll keep collecting reviews over time. Recent reviews are more interesting than 3-year-old reviews. but you still want to show aggregates and you still want to retain that data. So the bottom reviews microservice looks a little bit like TimeSeries data. You might even want to age out 3-year-old reviews or something because you don't care after 3 years, it's just irrelevant. And you put that into something like a Cassandra because, hey, what's the big deal if I lose a review? It's not the end of the world. It's bad, but it's not that bad. So you make that compromise. Except, how do you scale out your Postgres is completely different from how do you make your Cassandra work in production. How do you do a backup across these two is yet another story, right? So now let's come to the third one. You want to also sort your items based on very, very fast-moving dynamic data. Show me the items in the business category, like the business books or whatever, that were most viewed or most reviewed or have the highest rating. So these things change because if a lot of people like your product and write a lot of reviews, those numbers are going to change. And it's in your interest to actually show the correct answer because people will buy it more and people will think, hey, this is a great service. They're giving me great data, right? And how do you do that? People often put that in Redis, right? Because it has some great access patterns that are a lot more complicated to build in the app if you use any of the other databases. So you put that in Redis, except Redis is not sharded and it's not persistent. So now you have to make a decision on how important is that data. Yeah, you know what, page views, yeah, I'm okay, I'll leave that in Redis and maybe back it up to Cassandra because if something's lost, I'm okay. But instead of page views, if that's actually the number of people that wrote reviews, yeah, I might put that in Postgres because that's a little more important. So it becomes very nuanced and you have to figure this out when you're building the app, right? So the entire thing has to be figured out. And if something grows, ends up like getting really popular and growing by a 10x, it's going to be very complicated to scale this setup because there's a lot of dependencies between, right? So what's the alternative? What is the simpler approach, right? And a lot of us here, this is the genesis of why we started building YugaByte DB. It's what we had seen at places like Facebook, like we had seen the transformation from this world that we're talking about to something that we can go to and make it simpler. So our approach is that it's not the database, it's the API that matters. It's what you can do with that database more so than the actual database. So what can we do? If you can do what you can achieve with a PostgreSQL or RDBMS, which is things like transactions and secondary indexes, then you can use that data store to get your job done. Similarly, if you can do what a Redis does, giving you things like a sorted set, for example, to dynamically rearrange data according to very variable scores, right? So then you can pretty much store that in a database that scales and functions exactly like one that supports transaction and secondary indexes, and that simplifies your app development. Similarly, if something behaves like a Cassandra and you can actually model time series data and time partition, time sort it and partition it by various entities and so on and so forth and scale it out, that makes it that much easier to build your app. But it's the same uniform database. So if you want to take a backup, it's the same across the three. If you want to scale out, if there's a failure, all of these characteristics are the same. So that makes thinking about how to build an app and actually running it in production both really easy. Okay. Yeah, so what it really says is, instead of building to 3 different data sources or multiple different data sources, you get a single data layer that speaks multiple APIs with a common operational function. Okay, so we're actually going to look at a lot of the design patterns that we talked about, or the features that apps often need from databases, and look at how they're supported if you use a database like Yugabyte DB. So Yugabyte DB is multi-model or polyglot, whatever term you prefer, which means it speaks multiple languages, right? Because the query layer is really an abstracted, pluggable layer that can be extended pretty easily. And it currently implements 3 different APIs we have talked about: YSQL, Redis, and Postgres, which is going to come pretty soon in beta. But for the remainder of this presentation, because we're going to announce our 1.0 and our YSQL and our Redis APIs are actually quite powerful, we're going to focus on what you can do with just these 2. All right. So first thing is asset transactions. So we talked about, I have a bank account. A user wants to transfer $100 from his savings to his checking, or from his checking to another user's checking, right? You typically would have to model this on top of an RDBMS and have to put this remaining data about the user's profile in a NoSQL system, because that can be a larger amount and the access patterns can vary. What you see here is a Cassandra query language, for those of you that are familiar with how it looks, but it looks pretty similar to SQL. What this says is that I have a table for bank accounts. there is an account name, which would be replaced with an account number in a more realistic scenario, but for an example. And you have an account type. So things like savings and checking for a single user, or you could have multiple savings and checking accounts. And you have a balance. What is the total amount of money that you have in that account, right? And if you wanted to transfer money, so in this example, John is transferring about $200 from his checking account to Smith's account, right? So this has to be atomic, right? We don't want the bank to be losing money because there was a database glitch, or either of the bank users, the people who have the accounts, to be losing money because the database failed. That would be like really bad for the bank, right? So what this does is begin transaction, and then you can actually do your two updates and do an end transaction. And this is very similar to what you do with a RDBMS system, but this is supported with distribution, scale out, and so on and so forth in Yugabyte database. Okay, so that's one of the access patterns we talked about. Now, the minute you have ACID transactions, you can actually go and build secondary indexes on top. Okay, what are secondary indexes and why are they important? Most folks would know, but I'll just like mention it cursorily. We're again talking about an e-commerce like site or an online shopping site. Like, let's say you have a bunch of orders, right? A customer has ordered something that has a dollar value on a certain date, right? Now, because it is important to serve this data for each customer when they go view, like, how much did I order on which date, it's going to be optimized for lookup only by the customer ID. So if you look below, I tried. So if you look below, think in the double brackets, what that says is keep all my customer data together even if I add nodes. Okay, so that's the partition key. It says, like, I don't care what you do. If I add nodes, don't cut my customer's data and spread it across multiple nodes. The second piece, thing outside, is the clustering key. What that says is, for a given customer, keep all the data of his different orders sorted by time. Okay, so that means accessing all of the orders for a given customer in a time range is very, very efficient. Okay, now we've inserted some data. We just put some values in, and if you really want to figure out how much a given customer has ordered, that's an efficient query. Right? That's something the customer might actually come in and see, and hence it's modeled that way. But what if the store wanted to see how much did I actually sell across all my customers on a given date? Right? That's not optimal in the current layout, for which you create an index. You create an index on the order date. Right? So by creating an index on the order date, you'll be able to efficiently access data for each of the dates across all your customers. And so the second query actually becomes very efficient. Now, one of the problems with RDBMS systems is they're single node. So if there's a lot of those queries, it's going to be tough to scale it out. With NoSQL, the problem is that you can scale it out, but you don't have a consistent way of getting the actually correct answer. Like, your answer may be off a little bit because of eventual consistency failures and so on. And if you put the whole thing into a cache, it may be stale data. So there's really no way out, given the way things are today. But that's where Yugabyte helps. All of this works in a scale-out system. Okay, the third piece is a native document model or a JSON, handling JSON data. Now again, let's talk about our e-commerce store or whatever, and we're going to look at books, right? Now your books could have a lot of attributes. Like book 1 was written in some country and has like 20 attributes. Things like author, genre, name, year it was published, so on and so forth. But book 2 could have been published in some other country, or maybe it's simply a very old book and it doesn't have all those pieces of attributes. So in this example, book 2 does not have a genre, right? And you may find out what the genre is at a later point of time. You may find a completely different attribute that's very interesting to end users, right? So that means you need to be able to store flexible schema or JSON-like payload and be able to do native queries on top. Okay, so this is something that Yugabyte can do. So you can store this data and you will be able to do filtering to say, hey, give me all books that have the genre science, right? And it's going to filter out all the rows that don't have the genre science, and it's going to match exactly on rows that have a genre called science. Okay, another very useful feature from the database is to automatically expire data. So before we get into what this thing shows on the screen, I just wanted to give you a motivation for a couple of places where this is very useful. Again, back to our e-commerce store or online bookstore, you may want to run a discount on an item, and you may want to run it for the next 1 week, right? So you know when it starts and you know when it stops. Now, if you were doing this on top of a traditional RDBMS, you keep track of time, the start time. Every time you access, you go figure out, has it been a week? Should I drop this data? Should I delete this discount record? Should I flip it to inactive? Do something. But if you're embracing a NoSQL first approach, you can actually enter a record and say from 1 week from a certain time, from the time of entry or from a certain other time, you want the data to automatically be deleted by the database, which means that the database will not serve you that record after a week. That makes it very, very convenient and not have to have all these background processes figuring out which data to delete where and what the scale is, and did I miss something, and did some discount stay there forever and I'm losing money or whatever. Right? So you don't have to deal with all this stuff, which you would have to in a traditional RDBMS case. But the problem with NoSQL, again, is your consistency semantics, where you don't want to put your discount data there in the first place. So that's the trade-off, and that's the gap that this feature fills in the Yugabyte database itself. So in this example, what we did was we inserted a record, right? And we put a time to live of 10 seconds, right? And you it's a bad idea to have an employee for 10 seconds, but whatever. So the first time you do a select, right, you're able to see that you have all of the records inserted. If you do another select after 11 seconds, one of the records would have been expired, like Jack's record would have been expired. Similarly, and that was the YSQL API, but we have the same support in the Redis API also. What that shows is you can actually set a key, and Redis is used as a cache in a globally distributed fashion. So you want to serve data from Asia, Europe, US, everywhere, and you want to replicate this data. You keep your data in an RDBMS or NoSQL, but you then put it into Redis for fast serving across the board. And Yugabyte supports the Redis API, and it's really, really fast in serving your queries from Redis. So what you find is you can actually set your data with an expiry, and you'll find that that data actually expires after 10 seconds. Pretty similar to how a Cassandra would work, right? Or a YSQL API would work. Okay. Okay. The other thing that we did was, and this was a popular request in Redis, and we talked about this in the beginning, but going to go into a little more detail here. Redis, we found when it came to actually modeling stored data, as a database, was actually missing one of these APIs. And I believe Redis has more recently added it, but not at the time when we enhanced the Yugabyte database with a native time series type. So what a native time series type does is you'll be able to add for a given key, you can have a timestamp and a value, a timestamp and another value. So it just models itself as time series, but all of this data is persistent and scalable and so on and so forth, right? So you can actually pack it with a lot of data. Now, things that you can do with it are you can actually query all your entries within a time range. So give me all the data between some time T1 to some other time T2, and you'll be able to extract those records. You'll be able to delete entries. So you can go in and time series databases typically sometimes are not good at deleting data, or NoSQL databases resurface deleted data, so you wouldn't have any of those issues here. And finally, this is the other heavily asked for feature, which is Redis allows you typically to expire the entire key. So if you had written CPU usage at time 1, value 1, time 2, value 2, it will let you expire the entire key, but not each record relative to when it was inserted. Right? So that's an enhancement that we have done, which says I'm going to add a key, but expire this particular entry and not the entire CPU usage for everybody in some time, in an hour or so. And similarly, you can also say, I'm going to add it, but expire it at an absolute point of time. I'm going to be inserting 100 keys or something, and I don't care whether it's a day from now or 2 days from now. I want you to delete it on the 1st of May. And you would be able to achieve something like that. And that is useful again in a discounts-like case where it may not be relative, it may be absolute, finish the discount right after Black Friday or whatever. So. Okay, so the next access pattern that has become extremely common is you have your transactional data, but you also want to compute something on the side, which is real time. Right? A classical example, if you're talking about e-commerce, is personalization. So if you go to a site, it's going to tell you people like you who viewed this item eventually ended up buying some other item, right? Or based on your usage, buying, and browsing history, here are some items and discounts of interest to you, right? And how do you compute this? So traditionally, you would take this data, ETL it to a warehouse, and you'd run your jobs there, and then you'd ETL this back to the database, and then you'd serve this to the end user. Except if you do that, you're surely going to be out of business because Amazon does this in real time, right? Because that's the need of the hour. Like, incorporate more and more of the learning, the machine learning and AI into your responses to the users. And if you're doing that ETL, the user's like long gone before you're serving him the answer. That's like too late, right? And if you try to run this on top of a transactional database, RDBMSs don't support or scale for this, so it's just difficult to do that. And you don't want to take the risk of running this in your database that's serving end user requests, and fine, I'll give you the great insight, but the user can't buy the item anyway because the database is gone, right? That doesn't work either. So in order to do that, there is a set of use cases where you need to do this in real time, and the way Yugabyte helps you is you can actually take a replica of the data without an ETL process, run your machine learning real-time jobs using like something like a Spark or Spark Stream in real time on that data, write the results out back to the database and serve it in real time. So this forms a tight loop, and you don't have multiple different systems that have to come together for this use case. Of course, there are use cases where you just want to analyze a whole lot of data and it's not user serving. So Yugabyte is probably not the best suited thing for that. But the way we do this is we are completely API compatible with Cassandra, which supports Spark on top. So we naturally inherit that, and you're able to quickly set up an app that connects to a cluster that has Yugabyte. You'll be able to read data and write data back. You'll be able to write a fragment that will read your rows from a table, do your computation, and save it back to the serving tier, which can then get replicated across multiple geographies or what have you. Okay? Okay, so now we're going to go into those deployment aspects that actually affect development, and you have to think about ahead of time, right? Sometimes you have to think about these things even though your app doesn't particularly care about these requirements as features, but it still has to choose the right database in order to be able to achieve these features. So linear scalability, you should be able to deploy, and at the beginning you don't know if your service is going anywhere, but then it gets massively successful and a lot of people come in and everybody connects to the database dies, and your service is done. It's not a good story. So what you really want is the database to actually scale, and you should be able to change your machine type and be able to handle incoming requests at high volume, low latency. And this is something that we've done. Like the graph on the right shows. The graph on the right shows that we've tested Yugabyte at like 25 and 50 node clusters. We were able to scale it out linearly. It can handle a lot more, but at that point, we're just paying the cloud providers a lot of money. So if somebody wants it, we can figure that out. But the interesting part is we're able to do like 1 million reads at 25 nodes with 300 microsecond latency, and like about 2+ million reads and 1+ million writes, but at 200 microsecond latency. So our read latencies are really, really low. They start approaching sub-millisecond even when serving from disk on a public cloud. And similarly, these writes are replicated three-way and consistent writes. So that means if you lose a node, you will get the exact same data back from one of the other nodes. It's built to tolerate failures. The other aspect that's becoming extremely important is the ability to deploy across regions. Right? So let's take the example of this e-commerce app where the user has to log in. Like that's probably universal to every app today, like a cell phone app, like your phone or your website or whatever. Right? So what is required of an app that does user login? You want your users to log in quickly. That's the number one thing. It takes a long time, the user's gone. Like they go to another service, right? And you want your user password to be consistent. And you don't want to mess that up. Like people get really pissed off and definitely leave you after that, right? So how do you achieve that? You should be able to natively distribute your data because laws of physics kick in. If you keep your data in a couple of data centers and somebody from like a faraway region like Tokyo tries to access data where all the data is in the US, it's going to have high latency. It's just laws of physics. You can't do anything about it. That means you need to replicate your data. And Yugabyte lets you get to this setup in just a matter of minutes, right? Like it would have been months and months of engineering to get here previously, but very proud of the fact that we allow this sort of a deployment natively integrating with Amazon or any other public cloud. What this does is your writes that come from any data center are globally replicated and consistent, and you have the choice to read from your nearest data center, so you can get your microsecond level latency on reads. Okay, so we were talking about reads and getting low latency. Yugabyte offers you a tunable read latency. So let's take the example of a primary cluster where you have your actual core data. It allows to have a read replica or asynchronously replicate your data to a faraway region. Now, you have all the data that's sharded and replicating, so you don't have to worry about scaling out. You can scale out any of these things. You can change your machine type. You can change the zone they're deployed in, all of that with zero app downtime. Now, let's say you have an app or client, right? And your app can be dynamically programmed to choose from any of the following. You can do a read from the nearest data center. So I want absolute low latency, but I'm okay with timeline consistency, so asynchronous replication. You can go and read from one of the followers because you just want a lot of read throughput. You know, I don't really care, all the regions are closed, but I just want to be able to serve a lot of reads, right? And you can read from the leader, which will give you a response like a database. So with these combination of tunable reads, effectively, you'll be able to get the equivalent of a database plus a cache, but without having to manage two tiers. Right? Another thing, and increasing concern, don't be locked into a cloud. GCP is cheaper than Amazon. Microsoft gives you a better offering in some other, like, you know, in Asia or some other region. Some other service, like some companies, some developers are familiar with a certain cloud and want to build there. So multi-cloud is extremely important for a variety of reasons. And there's also regulatory reasons where, you know, only certain guys have certain data centers in countries where you're forced to keep the data locally. So you might have to go on-premise as well. Yugabyte supports Amazon, Google, Azure in the works on-premise, and we're working on Kubernetes also. And like in the enterprise edition, Yugabyte Community Edition runs in Kubernetes really well. That's the demo today. But it supports the ability to run in multiple clouds. And it's, again, minutes to get started with any of these things, any of these clouds. Okay, yeah, this was the thing about running Yugabyte in Kubernetes. So we have a YAML, we have a whole bunch of YAML for different configuration settings, like if you want to run on local SSDs, if you want to run multi-zone. So we're just like working with Kubernetes and figuring out the best way for you to deploy Yugabyte natively inside Kubernetes, because your app, a lot of people have deployed apps in Kubernetes and would love to have the data tier also in there. And we are like pretty cloud native in the sense we support Google Kubernetes Engine, Azure Kubernetes Container Service, Terraform, Ansible, so on and so forth. We'll continue our integrations to make it easier and easier for people to run in a cloud native fashion. Okay, so let's come to the real world example. So we looked at a lot of things that go into building an app. So we're now going to look at a practical deployment and, you know, how it really plays in. So Yuga Store is again an open sourced app. It's on GitHub, but we built it on the Yearn stack. So Yearn is Yugabyte, Express and Node.js for the REST API middleware, and React for the UI, right? And all of this is, the entire thing is running natively on Kubernetes using stateful sets for the database tier, and just like replica, deployment for the app tier. Okay, so the app itself, and we're going to take a look at that in a second. The app itself is an online bookstore app. What you find is there's a whole bunch of books. You can actually go in and see any of the books. So why don't I actually switch and show you guys the app itself. So this is the, hopefully I'm loud enough. Okay, so the app itself is a simple bookstore app. It's what you would expect. So there's like a bunch of books, right? And each of the books are categorized into static categories. So you have like business books, which are like one category, cookbooks, mystery and suspense books, sci-fi, and so on and so forth. And you can imagine a full-blown bookstore would have a lot more books, but it's so interesting to keep adding data for a demo. So And those are static categories. And then you have some dynamic categories. So we talked about this again, as we were seeing, like we talked about static categorization, but we said like there are some attributes that change way too often. So things like, show me the books that are that have the highest rating. Hello. Yeah, so there are some books that are dynamically categorized, like those with the highest rating. So if you click on that, you want to see books that have the highest aggregate rating. Similarly, like you might want to see books that have been reviewed the most, and so on and so forth. Right? And all of these attributes can change pretty quickly because another 10 people write reviews, something else is the most important. Right? And writing this into a database and having to say, like, another useful feature is to show you against the highest graded how many such books are there, like the count, right? And if you were thinking of modeling this on top of a traditional database, you would have to do a count star and fetch the latest count from a database, and every time somebody comes and writes a couple more reviews, like, effectively you have to redo the query. And it's either that your cache gets stale or your database is pretty much dying trying to answer these queries over and over again. But APIs like Redis help a lot. We'll look at that in a second. And then the final thing is you can actually click in on a book and you'll have a lot more attributes to display. So you show like some summary details and then you have a lot more detailed info. So that's the background on the app. So let's go back here. What we see is there are certain attributes that are not too dynamic, like the description, the title, what its category is, like is it a business book or what is it? Is it like a paperback or a hardcover? Those things don't really change very often. But you have very, very dynamic data, like the number of people that did the review or the aggregate rating or something. Right? So these are two different access patterns, and we use two different APIs in this app to actually build, which makes life really simple. How do we do that? Well, and again, we're going to connect and see this live, but the products are modeled as a table, like a regular SQL-like table, and because it's more familiar, right? It's easy to write that way when you have some sort of a structure around what you have. It's not completely unstructured. And if you just want to do something like show me a book in the business category, you can write like that snippet of the SQL-like command here, which says select a few categories from our Products table where category is business and limit 1. So it shows you one book in the business category. And similarly, if you want to do something that's more dynamic, you can use the Redis sorted set. So Redis sorted set, you can just keep adding entries with a score. In this case, the score is the actual rating or the number of stars or number of page views, and it's going to keep that in a sorted fashion by the score, and it's really good at keeping the total count of the entire set as well. So you could have created one set for all the products, and you could say num reviews is what I'm going to store in this sorted set, and you just keep adding the scores. And if you do a Z rev range, which is give me a descending sort, it will give you the top 2 books, because you want from 0 to 1. Show me the top 2 books that have been most reviewed. Okay, so what is the architecture for this whole app? How is it running, right? So the first thing is Yugabyte internally has 2 sets of services in Kubernetes. One is like the master, the YB masters, and the other is the YB tablet service. The master takes care of cluster level metadata. What tables do I have? If you want to create a table, if I want to re-replicate data, so on and so forth. And the other, the YBT server, takes care of the actual I/O. So this is the one that has the docdb, and it does replicate your data and houses different types of query languages and actually serves I/O. Now in this Kubernetes deployment, we have 3 pods, which are equal to 3 nodes, 3 VMs, 3 machines, whatever. And they're exposed using a headless service. The headless service is a way to discover how many pods or entries you have inside that tier. So I would need to know what the masters are, but the masters could be changing because I'd be changing the machine type, I'd be changing my configuration all the time. So it maintains a DNS-like name that can be used to query and discover the set of nodes inside. So that's the headless service, and a load balancer in order to expose the UI, the dashboard outside. The tablet servers have a headless service as well, so that you can actually discover the nodes that serve I/O and your clients can connect to it. Now, the other thing that we're going to look at is we actually have the app running, The app can also scale out. We're just going to look at a single pod for this example, but it can pretty easily scale out because that's what Kubernetes does. It scales out stateless apps really well. So you have a bunch of stateless apps exposed using a load balancer, and the end user goes through the load balancer to hit any one of these pods and view the app itself. Okay, the app itself uses this CNAME or URL to discover the nodes, and these nodes use this CNAME or URL to discover the masters. So that's roughly how the architecture looks. There's a lot to draw here, but it's just a couple of commands to get it running, right? So like a lot simpler in practice than the theory. Okay, so let's look at this in practice. So this is a view of the Yugabyte master dashboard. If I were to go back to this architecture diagram for a second, what we're looking at is this guy. We're looking at the load balancer that exposes the masters. Okay, so yeah, hopefully you guys can hear me. It's very inconvenient. So okay, so this is the IP address of the load balancer. We're going to look at where that comes from, and what you find is there are three masters or pods: master 0, master 1, and master 2. They internally form a raft group, so they come in and start replicating data and elect one of themselves as the leader, and if it fails, another elects itself as the leader, and so on and so forth. And they keep all the metadata highly available and like replicate. Now, what you find here is there is a table here, a user-created table, and Redis has a system table, so you can store Redis data persistently inside also, which is a yugastore.products table. That's the one where the data goes, and that's where some of the data is being stored from, the static categories and so on and so forth. If you go here, what you find are there are three tablet servers. These are the guys that actually do the I/O. So if I'm going back to this diagram, we're now looking at these guys. So the masters know about the tablet servers and are displaying it in their UI. So that's what we're seeing here. What we find is that there are some tables internally created in the system. Every table created in Yugabyte is automatically sharded into small chunks. Each of them is called a tablet. These tablets are replicated and they are evenly spread across the set of nodes. What we find is that the tablets for the tables that exist so far are evenly replicated across these three nodes. And currently, this guy is doing no I/O. There's really nothing going on there. Okay, so I just wanted to show the setup as well. It's just running in Google Kubernetes engine, but you can think of this as running on VM, bare metal, it doesn't matter, right? But this one is an example in Kubernetes. So what you see here is the same thing, but through the Kubernetes command line. What you see here is there are three masters, and there are three tablet servers, and there is one deployment of the stateless application. So, and you can create any number of these pods, and they'll be spreading out to multiple nodes. Now, let's look at where these guys are running. What we find is that the third number here represents the physical node. That's how Kubernetes gives IP addresses to pods so that you'll be able to find the fault domain on which it's running. So what you find is that the master is running on 6.3, master 0, master 1 is on 3.3, and master 2 is on 4.3. So you can actually ask Kubernetes to schedule your pods in such a way that they have anti-affinity, which means don't schedule two of my pods on the same node, because if the node dies, you lose all your data, right? So you want it to actually, each pod to actually be affinitized to a physical node, but not be co-located. Okay, so what else can we see here? So let's connect to Cassandra shell. So this is the YSQL shell. So we're connecting through that, and we're actually going to look at some data. So let's say you just wanted to see 3 items from the products table, right? It looks like select a whole bunch of attributes from Yugastore, limit free. Right? Looks like a pretty standard looking query. And that's going to give you back some of the data. And this is the way it's stored internally in the form of tables. Now, let's say like, hey, the business category looks interesting. Give me 3 books from the business category. So all I did here was add a category equals business. And you'll be able to pull out the data for all the books that have a business category. And then finally, we can say,
yeah, give me all the books that have both business and are hardcover, right? And you'll be able to run that, and you'll be able to see all the books that are business books, right? And that have a hardcover type as well. So these are the different kinds of views that an e-commerce app would want to expose to its users. But there's the dynamic views we talked about. So let's go into. We just connected using the Redis API, so the Redis on top of Yugabyte. And again, remember, this is a persistent data store. It's not a cache, so if you lose nodes, all of that stuff, your data is fine, it's protected. This is a view, this is a query that will give you, for all the products, show me the top 5 products sorted in a descending fashion, because it's reverse range, in a descending fashion by the number of reviews that they've had, right? And if you run that, and the which scores tells you, actually give me the review count also, right? So it's going to give you that number. Similarly, you can do the same thing for the aggregate number of stars, like this is the total rating, and so on and so forth. So that's pretty easy to accomplish, because you're now using the right API for the right job, but you don't have to worry about moving the data back and forth and doing a lot of stuff to actually get it to run in production. Okay, one other thing I wanted to show, we can actually run a bot clicker program. So let's, yeah.
Is it possible to join, let's say, have a product item table? Is it possible to join the table?
Right now, no, but we are working on that. So it is in our roadmap. So that we will put in the Postgres, the SQL side of things. But typically, in a like the other side is like if you think about a scale out system, you typically keep the data denormalized and replicated for fast access. So depending on the use case, you may be able to pre-join it and keep it in the right format for in a serving tier.
Okay. Otherwise, we can take a view or something, right? View,
like view, not enough, but those are things we will add.
Oh.
So yeah. Secondary index with covered columns, we have that, but that might serve as a view in some cases, but in other cases that we will add generalized views in the general program. Okay, so let's run this bot user. This user is just like clicking on a lot of items. So it makes the person running this app store look very good, like because it looks like a lot of people are visiting the site. But more interesting than looking good or anything, like here, if you now refresh, what you'll see is that the reads and writes are scattered across to different nodes, and the nodes uniformly take reads and writes. So that's what like you're able to see. Every time a user views a certain page, we update a whole bunch of records, like how many page views for that item, and what is the history, like what is the URL from which the user came in, and so on and so forth, so that we can actually feed this into a dynamic view, which says, show me the items that have the most views so far. And you may want to still further break that down into show me the items that have the most views in the last 24 hours or something. And that's where like a time series with a TTL type, all of those start helping. Now, let's do one more thing. So let's say that we actually want to scale the system out. So, because like it's getting really popular and everybody likes this. So okay, so I'm going to do that guy. What it will do is that it's going to bring up a new tablet server. If you remember, there were 3 of these guys, 0, 1, and 2. Now we have 4 of these guys, 0, 1, 2, and 3. So there's 4. And if we go in here, what we see is that a new tablet server got added, like in this system. So you will now be able to, I mean, as you get more requests, you'll be able to do this. You'll be able to change your machine type and so on. But the other interesting part is what you find is this tablet server starts taking a certain number of tablets and starts serving load almost instantly. So every piece of the data that it receives, it starts ramping up. So it gracefully ramps up to where all nodes get equal over a period of time. So if I refresh this, what we'll find is it will increasingly get more and more tablets or subset of the data across tables, whereas the entire system is running, your app is like completely functional. It's like, you know, viewing your users are viewing your pages and all of that stuff, and that's going on fine. And this thing is going to keep ramping up, like on the total number, and you will find that the number of reads and number of writes and so on are actually increasing. Okay. So I'm getting pretty close to finishing what I had to say. So either hopefully you guys have some questions and have a good discussion. Or yeah. All of this is open source. You guys can try it out on your laptop. Like it just takes a few minutes. You can deploy it. It will bring up multiple processes to mimic multiple nodes. You can do this in a variety of different configurations. We have an explore section that will walk you through what happens if you kill a node, when you add a node, when you want to do a transaction, when you want to do a secondary index, and so on and so forth. So we have a whole bunch of those. If you guys are interested in getting involved in the database itself, nothing like it. If you guys want to contribute, or if anyone is interested in contributing to the app, the sample application, which itself needs like a lot of improvement, like that's a journey in how people build applications, like that would be great too. So things like the app is still primitive and rudimentary, like we still haven't added things like checking out, which would need transactions, or actually having a separate microservice for each of the different access patterns. We haven't done that. Using different, like a Postgres API, we just use 2 APIs now. We could be using 3 to make it more relevant and simpler to build for the users, like you were asking about joins and so on. So as more and more APIs come up, like leveraging the power of those APIs and finally connecting it, like making it a more production-like deployment inside Kubernetes. So a number of things, like, and please feel free to reach out if you guys are interested. We have an online talk tomorrow also. Like it's at it's at 10 o'clock, and Sid, our VP of products, like is going to be talking about how do you deploy and scale apps which need transactional guarantees across multiple regions, so remote regions or whatever, with low latency. And he's going to be explaining about a few deployment choices that are available and what are the trade-offs and how can you actually get it done quickly, because at the end you have to have this running and you have to keep changing it over time. Like Amazon retired the C4 machine type, the C5 is current. You need to change your app or your database to actually utilize the C5 machine type so your costs are low. And that's like a huge process in itself. But with YugaByte, hopefully those things become far, far easier. That's all I had. So questions?